Hello, everybody. Thank you so much for the opportunity to talk to you guys today. I'm going to be talking about some ongoing work on the upcoming Prime Focus Spectrograph survey, which will be a multiplex spectrometer on the Subaru telescope in Hawaii, and then kind of going into the theme of the conference of the cosmic web. I'll be talking about Lyman alpha tomography, which people maybe have heard about or heard a little bit about. But essentially, it's a technique to try and reconstruct the three-dimensional high redshift universe. In my case, high redshift means redshift 2. And some work along those lines using what is known as dynamical forward modeling techniques to do that reconstruction. So to kind of give I guess I already said that. So the kind of fast facts for the prime focus spectrograph. So it's a multiplexed spectrometer on the Subaru telescope. Hopefully, it'll be coming online, I think, in mid to late 2024. And it has three main pillars, as we call them. There's the cosmology subgroup. So the cosmology pillar will be kind of in a similar vein to surveys like DESI, but going to higher redshift with its Galaxies sample and potentially higher density. And those are all going to be targets that are selected from the HyperSuprime wide. So this is a photometric survey that has been recently completed. Then complementary to the cosmology survey, there's the galactic archaeology component, which is a more local focus survey looking at the structure in the Milky Way as well as in the Andromeda galaxy. It's aiming to be one of the first surveys to actually do a survey of stars in the Andromeda and actually reconstruct some of the three-dimensional structure there from that survey. And then the main focus of this talk will be the galaxy evolution component, which is really focused on understanding the evolution of galaxies from cosmic dawn to the present, and how that evolution is affected by its cosmic environment, and of course, related to cosmic environment is the cosmic web. So in terms of kind of how this survey stacks up versus other ongoing and upcoming surveys, it's really trying to push to high object density in a high volume. So, you know, going big and going deep and going wide. So here we can see kind of the three main components here. Here talking about the IGM sample, which I'll talk a bit about, as well as the cosmology sample. And it's going to be over a wide volume. So hopefully getting some real statistical significance in its understanding of galaxy evolution. So this is kind of our favorite figure to show off in the Galaxy Evolution Working Group, kind of showing the various components of the Galaxy Evolution Survey. So at very real high redshift, not my fake high redshift, we have Lyman alpha emitters. I won't really be talking about these today, but there's a big goal to try and actually understand the dynamics of reionization via observations of these Lyman alpha emitters. I think there's be some more talks later on kind of about the physics going on here. The main focus of this talk will be the IGM tomography sample, or the Lyman alpha tomography sample. I'll be using the terms kind of interchangeably. And then if there's time at the end, I'll go into some of the low Z main plus deep sample. This is kind of aiming to do a spectroscopy of a large number of galaxies at this redshift 1, which I guess is now low redshift in the modern world. And I'll be hopefully talking about how some of my techniques could be applied to that sample as well. So the reason why we care a lot about redshift 2 is because it's what's kind of been termed as cosmic high noon. It's a peak of star formation. So by understanding how galaxies evolve in this epoch and how that evolution corresponds to the cosmic environment, we can hopefully really kind of pin together the early universe and the present universe and local observations. So the main probe I'll be talking about today is the Lyman alpha forest. I'm kind of going to assume people know about the basic physics of the Lyman alpha forest. You have absorptions by neutral hydrogen in the intergalactic medium. Generally speaking, this is best observed at redshifts of around 2, based on just the dynamics of the IGM. And normally people kind of think about these in terms of quasar spectra, and you can kind of think about them in terms of quasar spectra. I'll talk a little bit about using galaxies. But essentially, you have these absorption features, and you kind of can construct a one-dimensional skewer of redshift flux relationship, where you see absorptions, you have flux. And there's a lot of subtleties to this measurement I won't go into in this talk in terms of how you identify the continuum and overlapping absorptions, all these things. Let's assume that we have a one-dimensional skewer. And the idea of IGM tomography is we'll use a spatially close collection of these skewers to reconstruct the three-dimensional cosmic web. So in this cartoon, this is an idea that goes back to 2001 by Pinchon et al. You can imagine on the left here is some three-dimensional IGM simulation, hydrodynamical simulation. You can imagine if you have a grid of closely spaced sightlines, so you can imagine, again, these are just for the purpose of here, quasars. And if we're over here on the right, this could be kind of the picture we could reconstruct where the black points represent deep absorptions. And just by eye, you can play a connecting the dots game. You could hand this to a kindergartner and they could kind of draw the cosmic web just by connecting these things in various ways. And that kind of idea of connecting the dots, you can make slightly more statistically rigorous by talking about it in terms of a noise-weighted 3D map reconstruction, the Wiener filter. And then from these reconstructed maps, you could then relate that absorption to the dark matter, underlying dark matter structure, because at these redshifts, we expect this relationship, the Fleck-Schwingen-Petersen approximation to roughly hold. And I'll talk a little bit about potential deviations from that later on in the talk. So in terms of actually doing this kind of reconstruction, you really want to get a large object number density. And the issue with just using quasars to do this is that the quasar luminosity function kind of flattens out as you go to fainter magnitudes. But some work by K.G. Lee showed you could actually use Lyman break galaxies to do a similar reconstruction. And as you go to fainter magnitude, while the quasar luminosity function flattens out, this Lyman break galaxy function, you just keep on getting more and more objects. And so for the prime focus spectrograph, while we do expect to find some number of quasars, really most of our sources will be from these Lyman break galaxies. So the particular technique that I've been working on the past few years, I call TARDIS, the Tomographic Absorption Reconstruction Density Inference Scheme. And like the box in Doctor Who, you can travel through space and time, understand what the structures we observe, understand what the distant past holds for structures we observe. And the way we do that is through an iterative optimization scheme. So this is kind of the core of the dynamical forward modeling framework, where at every step of our iteration, you can imagine we first generate an initial density field. This is some random Gaussian field corresponding to our cosmology. We evolve that initial density field forward to a final density field. Final, in this case, is the redshift of our observed structures. So for Lyman alpha forest will be redshift roughly 2 to 2.5. This is done with a particle mesh solver, so literally kind of solving dynamics of the field. From this final density and related velocity field, we can paint on our target hydrodynamical quantities. So this, we just use Fleck-Schwingen-Petersen approximation. You could be more nuanced with it. You could use machine learning methods to perform this painting as well. If you're not interested in Lyman alpha forest, but are instead interested in galaxy fields, you could use your bias model or your semi-analytic methods to paint on the galaxies. You have a lot of options here. Also, because you have the velocity field, because again, you're solving the dynamics of the field, you can also just perform the redshift space distortions at this step as well. Then from these hydrodynamical quantities, you can map it into data space, meaning actually pick out the areas that you've observed, pick out your sight lines, pick out your one-dimensional skewers, and perform a likelihood calculation. Here I just show, a mean squared error type of likelihood calculation, comparing the flux observed to your reconstructed flux. And then because every step throughout this circle so far is differentiable, you could use a Newtonian or semi-Newtonian optimization method to refine your guess on the initial density field. So you can make an update to this initial density field. You can perform this, order hundreds of times fairly rapidly. So here's going to be a little animation showing this in process. So on the top, we have our simulated true initial density field, our simulated redshift 2 density field, And then down here will be our reconstruction in progress, the initial density field and the Redshift 2 density field. And then just to kind of make this concrete in terms of our data we're using, here the blue dashed line shows our simulated observed Lyman alpha forest. So this is Lyman alpha forest plus noise. And then the blue is the actual true Lyman alpha forest, or the true neutral hydrogen along the line of sight. And then this orange line will be our reconstructions. This is just picking out one sight line. I think here I use the prime focus spectrograph densities and noise properties. So now we can see this in process. As our optimization goes, there's an annealing process to better refine the source, the optimizations. That's why you kind of see occasional jumps. But overall, as the optimization continues forward, you're reconstructing larger scales to smaller scales. And hopefully you see that our TARDIS reconstruction better matches the actual simulated mock Lyman alpha forest better than the noisy data. It'd be sad if you're just fitting the noise. But here, because of the dynamics, the fact you're constrained to configurations that could actually evolve gravitationally, because of this whole particle mesh solver, you end up with a really good estimate of the underlying density field. And so you could use this for a lot of fun science. So one kind of thing I highlighted in one of the recent papers is you could actually make a really rigorous definition of protocluster using this. Protoclusters are all the rage. And here you could actually, because you have the initial density field, you could actually just keep on evolving that forward past Redshift 2 all the way to the present day and pick out your clusters with your favorite friends of friends finding algorithm or your spherical overdensity algorithm to actually reconstruct the initial density field. And similarly, you could use this to identify the cosmic structures with a deformation tensor approach, or with disperse, or any kind of other algorithm you're interested in using to do cosmic web identification. So now we can actually apply this to data. We don't have prime focus spectrograph online yet. It would be really cool to be able to do this on huge fractions, well, not huge fractions of the sky, but significant fractions of the sky. But right now we have a little pilot survey that KG Lee kicked off a little less than a decade ago, and now we have the most recent data release. So here is our little patch in the sky compared to the moon in the sky. This is in the cosmos field. Each of these little boxes represents a sightline, either a quasar or in most cases a Lyman great galaxy. The red dashed line is data release 1, and then this is the expanded data release 2. Not a huge sky fraction, but now as we're gearing up for the prime focus spectrograph, the focus is on technique SPAD as opposed to just expanding this existing footprint. And for the Komodo survey, we're having a mean separation of roughly 2 megaparsecs. So that is kind of our limit along the transverse direction of how well we can identify structures. You can push a little bit below 2 megaparsecs because if you use techniques like TARDIS, you have the dynamical evolution. So you could sometimes infer things on smaller scales, but the statistics trying to infer things on 1 megaparsec scales becomes quite difficult. So even with data release 1, we were able to identify some cool cosmic structures, some protoclusters, some voids. And this was at the time the highest redshift void identified, still is the largest void identified. And as well as other protoclusters which were identified or independently confirmed via various other methods. So with data release 2, we expanded this field by roughly 50%. This is the flux. So this is not with TARDIS yet. This is just looking at the flux compared to the galaxy survey. So up here we have the Hyperion cluster. Over here we have that big void. We have other smaller protoclusters more nearby. But then we can also apply TARDIS to this to actually reconstruct the density field rather than just the flux field. And so here's a slice of the density field. So at the top here is the Wiener filter reconstruction with just, again, the connecting the dots sort of game, or fancy connecting the dots. The middle panel, we have the TARDIS reconstruction. So this is the actual dark matter density field that we reconstruct. And In addition to using the alignment alpha force, we also included some galaxy information in this as well. If people are interested in kind of the dynamics of that, feel free to ask me at the end of the talk. And then we can use the deformation tensor approach, like we heard about this morning, to reconstruct to identify the cosmic structure from the dark matter. And so here, kind of in a cute little color scheme, I show the filaments and the voids and the clusters. We also have a nice little animation here showing that as well. So here again, I color-coded it. This is a discrete classification. So here the red regions are the clusters, the empty regions are the voids, and in between you have filaments and sheets. So playing this forward, we can see now the real 3D cosmic web. So kind of the combination of expanded footprint plus the new data allow us to really show this full 3D cosmic web in quite a lot of detail. So with these, beyond just making pretty maps, I love making pretty maps and pretty animations. Other people care a lot about the science of these maps. So we could, there's a lot of talks that are later on in the sessions discussing this. So Rico is giving a talk on Wednesday, looking at correlations between the galaxy star formation properties and the reconstructions. And then Benjamin Zhang on Thursday is actually showing forecasts as well as identifications of intrinsic alignments in hydrodynamical simulations. And another thing to highlight, which isn't a talk but is a poster to check out, is some work by Chenzhe Dong on looking at where this FGPA approximation really breaks down and where we need to really expand our understanding of the IGM modeling. So here we have an example of this is the COSCO1 cluster. So this is a cluster that was identified via the galaxy field, really with high significance. And then when we look at the IGM absorption, it doesn't really show up at all. And so this is kind of an interesting example where perhaps there was some early heating of this cluster that resulted in a low neutral hydrogen fraction. And so if you're interested in hearing more about this, take a look at the poster. And just in the final minute or two, I'll also highlight the fact that these same techniques could also be used for lower redshift samples or only with photometric data. So again, we can perform initial density reconstruction, but then at the last step, where before we were looking at just a mean squared error of our field, you could then expand that to various Poissonian likelihoods and actually be able to reconstruct the cosmic web using, say, photometric samples or other tracers. So here I show a nice little example of this. The goal was for the low Z main deep sample. So this is Redshift 1 sample, the prime focus spectrograph, where we were trying to see, could we actually reconstruct the cosmic web using a combination of HSC photometry, so there's a lot of galaxies with photometric redshifts, plus a few uniformly sampled spectroscopic samples. So here you can see if you only use the spectroscopic samples, you get a really coarse reconstruction of the cosmic web. If you only use the photo-Z samples, again, all within this dynamical forward modeling, you kind of get a slightly diffuse model of the cosmic web. There's some, difficulty in understanding exactly where clusters are. But then when you combine the two, you kind of get a synergistic reconstruction where you have the spec-Zs to kind of pin down large structures. And because, again, we have this whole dynamical forward modeling approach, we're constraining it by gravitational evolution, this really helps you understand where the filaments are, where the clusters are, where the voids are. And you end up with a much more accurate reconstruction. So hopefully this paper will be coming out relatively soon. So excellent timing. Yeah. So here are my conclusions in the last minute. So I think that hopefully you guys got across that PFS will be a really great tool for understanding the relationship of galaxy evolution and formation across cosmic time, going from Redshift 6 to the present day. That Lyman alpha tomography in particular is a really great tool for understanding these cosmic structures on relatively small scales, order a couple megaparsecs. And as we go to next generation surveys, you could push this down into order megaparsec or less. And that when you combine these kinds of techniques with dynamical forward modeling, you can really reconstruct a very accurate picture of these maps. And something I didn't kind of get into because we're cosmic web, not cosmology, But kind of just generally, these initial density constructions could be a really powerful tool for cosmology, because you're rewinding the clock back. All these nonlinear structures that people construct summary statistics about, peaks, topology, high or bispectra, all kind of get rolled back into just the power spectra. So if you're actually able to do these initial density reconstructions for galaxy samples with high accuracy, understanding the bias properties, this could actually give you all the cosmological information in one spot. Okay, and with that, I will hand over for questions.
Oh, the two. Okay, sorry. Maybe you first this time, and then try.
Yeah, thank you very much for the presentation. You mentioned just like your last sentence, I guess, the fact that you're trying to reconstruct the initial conditions. Mm-hmm. How do you make sure that the initial conditions you're reconstructing are not very unlikely? In that sense, you're putting some priors on
yeah, so in this case, we're assuming lambda CDM, so kind of everything I was showing was assuming lambda CDM, and in fact, specifying the cosmological parameters, so like omega m, sigma 8, etc. So that prior, I guess, is doing a lot of heavy lifting here. If you were interested in specifically cosmological analysis, what you could do here is, in addition to reconstructing the initial density field, you could also reconstruct jointly the cosmological parameters, and then do a statistical analysis on those reconstructions to figure out what the relative likelihood is of the cosmological parameters. Does that answer the question?
Right. Also have a question relevant to the reconstruction side. Mm-hmm. So as far as I understand, the observation side, what we have for the Lambda Alpha forest would be just some flux.
Will be some flux, yes.
Yeah, so in the simulation, you have delta directly. So there's a mapping between the flux tau
yes.
into delta.
Yes.
I wonder to what extent that uncertainty was accounted for in this reconstruction.
Yeah, so right now, kind of an analogy, right, with the cosmological parameters we hold fixed. We currently hold the parameters defining this mapping, the Flex-Ring-Gunn-Peterson approximation. It's like an exponential mapping on top of the density field. We're currently holding those fixed. We have played around with varying those, and it ends up not affecting the reconstructed cosmic web significantly. But there will be regions, for example, that high-density protocluster, where we might expect this mapping just break down completely because of heating from galaxies, heating from early shock heating, AGN activity. And so we're working now on making this mapping more accurate using machine learning techniques primarily. So I've developed this code, hyphy, I call it, which maps from dark matter probabilistically to hydrodynamical fields. So you could actually, from a given dark matter field, you can kind of see all these different realizations of the hydrodynamics based on the variations in shock heating, based on the variations of AGN activity. And this code works such that if you have your own favorite hydrodynamical simulation that you think reflects the real universe, I could throw that in, train the network, apply it to the fields, and then generate a reconstruction, initial density reconstruction, conditioned on that particular hydrodynamics that you think are the real hydrodynamics.
That's cool. So basically, the tau and delta mapping will be introduced as another layer of kind of machine learning.
Yeah, exactly, exactly. Yeah. And yeah, the hope there is that maybe if you want to marginalize over all hydrodynamical simulations, you could actually train this on all hydrodynamical simulations you want, and then do that same kind of procedure as well. Yeah. Or if you have your other favorite mapping that isn't machine learning based, your own like analytical mapping, we could theoretically include that as well.
Cool, thanks.
Yeah.
I'm trying to understand how costly things are. Are you running a hybrid simulation every time?
Yeah. So.
What's in hybrid simulation?
Oh yeah. So right now, kind of related to his question, right now I'm not running a hydrodynamical simulations every time. I'm only running this particle mesh simulation. This is n-body only. And then on top of that n-body, you then paint on the hydrodynamics using some kind of semi-analytical method. Right now, the blocks I've been showing here have been 128 megaparsecs cubed and running the particle mesh simulation at roughly 128 particles. So this is a very coarse simulation. Because again, even if we could reconstruct this dense environment really accurately, we don't necessarily trust the hydrodynamical mappings that we're applying on top of it. There's work currently underway to push this to higher spatial resolutions for the n-body, and then also, again, improving, hopefully, this hydrodynamical mapping. You could, in abstract, try to replace both of these steps with a hydrodynamical simulation. As far as I currently know, there's no really differentiable hydrodynamical simulation with respect to the initial density field. And doing this differentiably is really important because you want to be able to do this optimization. If you were able to do that, if there are simulations out there that have worked on this, that would be really cool. It would certainly, just running a hydrodynamical simulation is, of course, very computationally costly. If you have to run 200 of them, you know, that's certainly going to take quite a while. I am working with one particular hydrosim, NIX, which is developed at LBNL, which is kind of focused on Lyman alpha forest in the context of cosmology. And for that, we actually could run pretty large simulations in order a couple hours. So if we're able to make those differentiable, then you could theoretically do this full reconstruction fully hydrodynamically in order, you know, a week, say, which is fine. I would consider that acceptable. But most of the hydrodynamical simulations I know would be of order, you know, years to run.
So I understand how you do it for fixed cosmology. How can you really constrain cosmology? You don't know things like ionizing backgrounds, right? So luminosity is degenerate with omega.
Yeah. So yeah, varying UV background would certainly kind of complicate this quite a bit. In that, yeah, I think if you don't have a really strong prior for your varying UV backgrounds, that would certainly mess things up quite a bit. I think you would certainly have to apply some kind of model there. What is nice is that because you are running the full n-body simulation, if you do have a model that says, hey, at Redshift 8, if you have this kind of dense environment, you expect to have these ionizing bubbles, you could still include all those forward in your reconstruction. I don't know if right now the understanding is good enough to have people have trust in that kind of modeling. But then with galaxy fields, it becomes a little bit more clear because, you know, there's certainly lots of bias models of galaxies, and you could theoretically marginalize over those bias models to do this kind of reconstruction.
When you go from when you go from n-body to hydro, essentially, you're of course putting a lot of assumption into what the ingredients to, for example, paint a galaxy are. And for example, if you paint galaxy just based on the dark matter mass and the local density, you're effectively erasing any effect of the cosmic web. So how, and if you then use that to reconstruct the cosmic web, you're going to reconstruct the cosmic web as if it had no anisotropy, for example. How do you go around that problem?
Yeah, so for that type of problem, I guess the answer is that you could, if you have, say, you know, a lot of bias models have strong like tidal shear components, for example, that are fitted as well. And you could calculate all those kind of fields that you'll use for your n-bias model from your final density field, your density field here. And so then you could include those in your bias expansion and to predict your galaxy field. One of the eventual hopes is actually to be able to do a friends of friends finding algorithm on this field and actually find the halos and then paint in the galaxies based on whatever kind of property your model wants. So if you have, say, assembly bias, if you have some strong cosmic web determination, usually those properties should be able to be identified in the dark matter fields, either at this, you know, Redshift 2 or maybe in some earlier Redshift slice. And so then you could include those in the reconstruction in your galaxy field. As of right now, those are not implemented, but you know, there's nothing I think fundamentally difficult in that case.
We're exactly on time if there's no more questions. So let's thank them again.